Alright, going into more problems. 65 is the next one. There was like a ball or something, some kind of sphere or ball hanging from a wall in the picture they gave us. Find it on here. Too far. There we go. Alright. Says a solid uniform 45 kilogram ball of a diameter of 32 centimeters is supported against a vertical frictionless wall by a thin 30 centimeter wire of negligible mass. Draw a free body diagram for the ball and use the diagram to help find the tension in the wire, and also how hard does the ball push against the wall. So let's first worry about the tension and free body diagram and see where we could go from there. Alright, down below, free body diagram, this thing has weight. Weight's always down, right? The tension in the cable, it's the one thing that's at the angle. So the tension has two pieces to it. The tension is obviously holding it from falling, right? But it's also holding it up against the wall and like into the wall, okay? And the wall is a surface that the ball's pushing on, so the wall would have a normal force pushing back on it. Okay, so there's all the forces that are present. And from what was given, from here to here, you could see in the book was 30 centimeters. But it also told us the diameter of the ball was 32 centimeters, therefore the radius is 16. Okay? The reason why it gave us these numbers is because we need to find the angle involved. So if this is 30, if we just create in our diagram a right triangle there, if this is 30 and this is 16, that's 46 along this side. So I pulled out a smaller triangle over here that represents this. And from here to here, that would touch perpendicular to the wall, would also be the radius, right? So that's another 16. So I have a triangle that connects at the angle the rope is up there that we'll need for the tension that we split up. We could use SOHCAHTOA, sine of that angle, if that's the reference angle, is opposite over hypotenuse, 16 over 46, so we get out a little bit over 20 degrees, 20.4 degrees. We also, we're given the mass of it. Of course, if we know mass, we could take 9 times 9.8 to get the weight of it, so it's 45 kilograms. That got cut off there. It looks like that was 441. When I use it down here, it looks like when I scan this, that should be a 441 right there. Alright, so finding what was asked first, finding the tension in the wire. So let's do Newton's second law, summing up all the forces on each axis. This thing is in equilibrium, so we can set them equal to 0. So we have on the x-axis the horizontal component of tension pointing to the right, and the normal force pushing back on it to the left. So when we subtract those two, since they're the only two, they have to equal 0, therefore those two are balanced. And now that we found that angle, we could say that the x component of tension is Ft, the overall tension, times the sine of 20.4, and the normal force, that will give us the normal force. Excuse. Oh, actually, I'm sorry. I did this a little backwards. At this point, oh, I'm scratching my throat. We would have to stop here right now, because I don't know tension. But on the y-axis, I can find tension and use that to find normal force, which is what part B is asking. So the only forces on the y-axis are the y component of tension up minus the weight down. And the y component of tension is tension cosine of 20.4. And we could solve and isolate for tension because we found the weight earlier. And divide those numbers and get the tensions just shy of 471 newtons. Now at this point, we could go back over excuse me. We could go back over here and pop it in for tension right here, leaving me normal force the only unknown. Plug that in, run the numbers, and we get out a normal force of the wall pushing back on the ball of 164 newtons. You okay with that one? All right, the next one we got is 92, 97, and after that, if you have any more, we can answer them, okay? All right, 92. Looks like we have an Atwood system again. And I drew again a free body diagram for every box, but from the original diagram, you could see that block A is underneath a block B, and block C is the hanging mass. So it says in the problem, block B with a mass of 5 kilograms rests on block A, which has a mass of 8 kilograms. So this one's on top of this one, which in turn is on a horizontal tabletop. There's no friction between block A and the tabletop, but there is between the two blocks. It has a coefficient of static of 0.75, and then a light string attaches to block A passes over a frictionless, massless pulley, and block C is suspended from the other end of the string. What is the largest mass that block C could have so that blocks A and B will slide together when the system is released from rest? So this one's kind of tricky. It's why it's a 3-dot problem. But what they're basically asking us in this one is how fast could this system accelerate, okay? With the mass, what's the mass that can make this thing accelerate in such a way that we're just right at the breaking point, all right? So it's that main concept we have to grasp before really anything else. All right. So with that, we got to solve for that mass and include the max static friction, which we can use as an equality because we are going to assume we're at the breaking point. So if we set up the sum of all forces on the x-axis for block B, the top block in the diagram, the only horizontal force on it is static friction making it go forward. Be careful on this one because the tension is only directly connected to block A. The reason block B is moving along with block A is simply and only because of the friction. If this system accelerated fast enough, block B would slide off the back. So block B wants to slide to the left, and that's why static friction is to the right. Right? Friction always opposes the way something's sliding or trying to slide. So that's the first thing we got to realize in this one, on this block. So on the other block, block A, we only have tension to the right. Remember, we're ignoring friction between the block and the table, it told us to. And then we could also sum up the forces on this block in a moment, and it equals the mass of just C times the acceleration. And what we need to realize is all these blocks are together, right? So once we do specifically break up the exact forces that we're showing up here and plug them in for the sum of all forces, we need to realize A, and all three of these equations represent the same acceleration. If they're all connected, they all got to be accelerating at the same rate, right? So we'll remember that as we go. So now let's go and plug in the specific forces that we identified up above. So we'll call to the right positive, and don't forget it gets redirected on the pulley as it goes around. So we have the static friction, and I have a little note here. We're plugging it in as an equality because of the fact we want to eventually solve for something where this is at its breaking point. So that means μs times the normal force, and equals mass of B times the acceleration of the system. Mass of just block B on this one. And the normal force is the weight of block B on this one, because it's the top block. So when we plug all that in, we have enough information just from Newton's second law on block B to find the acceleration of the system. As we pointed out, that acceleration occurs everywhere we see it in any other equation because the system's all connecting. Now let's go to block B. Block B on the y-axis is what formally let us know the normal force, which I used over here. There's no pushers or pulls at angles, so all I showed in this step was the fact that this has to equal the weight of block B. That's 49, and we used that for the normal force here. That allowed us to get the acceleration of 7.35 meters per second squared. Now we go to block A. The only force in the sum of all forces on the x-axis for that was tension pointing to the right. But we have to use it equal to MAB, the combined mass, because that tension feels like it's just pulling one heavier box since block B is on top of it, right? So we got to be careful we use the combined mass of both of those, but we could plug in that 7.35 here. We do have the masses, I believe, of these. Yeah, 8 and 5, I believe it was. 8 kilograms and 5 kilograms, so that becomes 13 times 7.35, and we get a tension of 95.6 newtons. Now we go on to block C. The only two forces on block C were the weight of it and the tension on it. And remember, we continue positive around the pulley, so it's the weight minus the tension equals the mass of C times the acceleration, that same old 7.35. And now we finally have an equation where we have the unknown we're looking for, mass of block C, and we have no other unknowns once we get this far, so we just isolate it, plug in the values from some earlier steps, and figure that if the mass of block C is 39 kilograms, that will cause all this to happen based off this being the breaking point and using that as the breaking point. And this step here allows that to be the mass necessary to do all this. Basically, another way to look at this is if we had a mass that was any higher than 39 kilograms, that would actually cause the block B to slip off of block A. Because that would also cause a higher acceleration, and it would all snowball into the fact of working backwards, that it would come out that wouldn't be enough static friction to hold it on. Okay, on this one? Okay. And other one we have here in 97, and it's another system on an incline. And this is kind of like a unique problem, but it's a good problem. And we have to really focus, make sure you're looking at the original diagram of the book to start. Because what we have here is a block A, we're going to call block A, on an incline. But there's also a block B, which is held to a vertical wall right here by a string. And block B is going to help apply a frictional force that does not allow block A to slide. So there's not just friction between A and here, there's friction between B because block B is connected somewhere up here. Alright, so it's a kind of a weird system. But let's look at the specifics. Block A with weight 3W slides down an incline plane, sloped at an angle of 36.9 degrees down here. Oh, and it is sliding in this problem. It's not still. I might have said it was still before. It's sliding, but it is sliding with constant speed. Therefore, we could say the acceleration is 0. While plank B with a weight W rests on top of block A, this plank B is attached up here with a cord to the wall. So in part A, it simply just wants us to draw a diagram of all the forces acting on block A. And only on block A. So if it's sliding this way, remember what's trying to pull it down the hill, as always, is the X, or in other words, the parallel component of the weight. And in this direction, we got the perpendicular component of the weight, which has to balance out with the normal force. And the normal force, though, this is where it gets a little weird here. The block B is on top of block A during all this process. So the normal force has to push back with the perpendicular component of weight A plus B. So that's why I remember that block A is 3W, block B is W. So the normal force feels all that pressure, basically. And that's why we have to combine those. And using the formula for the perpendicular component, we add those up and we get an expression for W cosine theta, which would equal the normal force here. And over here, we would have block A is the only one that's allowed to slide, right? Block B is not sliding, or not allowed to slide because it's being held up, so we only use block A's weight to calculate the parallel component of it, which was 3W. That was another tricky part of this one. And we also have two frictional forces pulling backwards on this thing, or up the incline, opposing the sliding. We got the kinetic friction between the block A and the slope they define as S, and then between the two blocks A, B up here. And it does tell me then in part B, if the coefficient of kinetic friction is the same between A and B and S and A, determine its value. So I wrote that down up here. That means the mu between here and here and here and here are the exact same value. Therefore, I'm just going to use mu K without subscripting it anymore, since it's the same between both. All right, so after identifying all those correctly, that was a key step to number one. This one's kind of tricky. Now we can go to Newton's second law. It is sliding constant and on the horizontal axis, and it is obviously at rest on the y-axis, so we could all set everything equal to 0. So on the y-axis, that means what I kind of stated already up above. We got the normal force up of A plus B minus the perpendicular component of weight for A plus B, because this axis feels the total weight into the incline. Therefore, the normal force has to equal that. We already showed that the perpendicular component would have to be, of the total masses, would have to be 4W cosine theta. So that's where we kind of have to stop for the moment and use that in a second to sub. So it'll get kind of messy here, so try to follow. Now we go to the x-axis. We got three forces. I'm going to call down positive because that's the way it's sliding. So we have this parallel component of just A, because it's the only one allowed to slide, which is 3W sine theta, minus the two frictions. All right? And each friction is mu K times the normal force. But here's where we got to be careful. Yes, we stated that mu K was the same because it told us so for both surfaces, but the normal force is different. All right? The normal force for this friction between A and B is only due to the perpendicular component of weight B, because it's on top. So that's another place to be careful. And I will have to find that, and I did below. So I'll come back to plugging that in. And then the other friction here between these surfaces, the normal force is that combined, which we found in this step. Okay, because it's feeling all the pressure of both of those blocks on top of each other going into it, where this friction only felt the weight of the top block. I actually did do a free body diagram right here, even though it didn't ask, just for block B. Just to confirm that that perpendicular component of it would balance out with this one. So when we do the sum of all forces on the y-axis for block B, object B, we see that the normal force does equal that, just that perpendicular component of B. So now I could sub in W cosine of that angle, because object B was defined as weight W, into here. And from my first step, I'm going to sub that into here for the normal force, and that's still all equal to 0. Remember, my goal is to solve from UK. Every single term has a W in it, so it could divide out. And with some rearranging and isolating UK, we could plug in really just the angle and find that it is 0.45. So that was a pretty tricky problem. That's a lot going on and kind of a weird situation. Spencer, do you have any questions on that? Okay, you have any other ones? That's the last one somebody from at home asked me.
Yeah, I got 37.
37? Okay. Alright, two crates connected by a rope lie on a horizontal surface. Crate A has mass A and crate B has mass B. The coefficient of friction between each crate and the surface is mu k. That's same for both of them. Okay? The crates are pulled to the right at constant velocity by a horizontal force F shown in the diagram. Draw one or more free body diagrams to calculate the following in terms of MA, MB, and mu k. And then let's
I didn't know UK was in
the same in both. That's all right. We'll still go through the whole thing just in case anybody at home had any issues with this one. And we're gonna, for part A, we're gonna calculate the magnitude of force F and then the tension in the ropes connecting the blocks. So, although this system is not an Atwood system, it's a multi-mass system connected. And the best way to go, I'm not saying it's the only way, but I would say the best go-to way anytime you have a multi-mass system, Atwood machine or not, is to do a free body diagram on each individual mass. Okay, so that's how I started this one, and I know that it's a constant V. So anyways, on block B, we have that applied force they just call force F. And the tension in the cable that hooks them both together is pulling backwards on it. And we have its friction as well. And then on the y-axis, we simply just have the weight of block B and the normal force. Then block A is the one in the back. Block A is also feeling the tension, but the tension pulls forward on block A. All right. If you look at this system combined, not separately, but combine them, tension is an equal and opposite force on both masses. And that's what Newton was really talking about in his third law, that there is always an action and reaction, equal and opposite. This tension is acting on both objects, okay? To the left on one, to the right on the other. And so this tension pulls along this way, and friction still goes to the left. Friction always opposes motion. And then again on the y-axis, these two forces have to balance, the weight and the normal force. All right, so I'm going to first perform Newton's second law on the x-axis for block B right here. And we got F, we'll call that way positive, makes sense, minus tension minus FFK. Alright, so that equals 0, and the first goal I have to do is find is the magnitude of F. Now, I could isolate F right now, but that gives me some things that I don't know. We do know that mu is the same. I don't know a whole lot more. I don't know tension. So I need to sub that out. This is one of those problems where we get expressions in our answers, okay? So we got to get it as trimmed down as possible. So we want to find an expression for F that has as little amount of variables as possible. And leaving it like this, I would have an expression for F just moving all this stuff to the right, but there's stuff I could get rid of. So I'm going to just freeze on this right now and see if I can come back and plug other things in. Also, one little thing I did was proving the fact that the normal force must equal the weight, and the weight's m mass b times little g there. All right, let's go to the other one. Same thing already on the y-axis, equilibrium on the y-axis, which shows this has to be equal to that. That should be easy. Then we got the tension minus the frictional force, kinetic on this one. Therefore, the tension equals it and balances it. And I know friction is mu times the normal force, which I found right here. So I sub that all in. Now I got an expression for tension. And now I could sub it out in this one as I pointed here. All right, so from this step, this tension turned into this because I subbed that. All right. subbing that in and cleaning it up a little mathematically. The most I could do here to clean it up mathematically, I could move these two terms to the right, which I did by addition. And since both of them have mu k, since it was the same for both, and little g in it, I could factor it out, and this is simple as it could get. So I get an expression that has force equals mu kg ma minus mb. And yeah, you said, Spencer, you didn't realize that mu k was the same. If it was different, then we really couldn't go past setting it equal to those two terms. We couldn't crunch them any further and like factor it out. But it would still be pretty similar to that. Just that mu k would be like mu k a, and that would be mu k b or something like that. But we don't have to separate them because they told them this is the same. So we okay on that one? Okay. Any other ones? We got time if we need them. 45, okay. Did I sign that one? No, I didn't assign that one. You might have wrote that down wrong. Because 45 is a circular motion one. And we will get to ones like that. But I didn't assign any out of that section. So you might have just accidentally wrote that. Any others?
Did you assign 100? I don't think so. I looked at it, but I didn't.
The 100's also going to be one that will eventually be assigned.
That's what I thought.
There were some that were solved in this that I told you guys I didn't assign because they deal with circular. And we're going to do like circular motion as its own separate topic and have our own little like test on it.
I didn't do this one because I was like, that doesn't look like something.
Yeah, we didn't do that yet, so that's a bank curve one, and there's a lot of stuff in it that involves like things like have been doing, but there's also extra stuff in it that we didn't get to yet. I think the last one I gave was probably 101. Yeah, it looks like it. But anything?
Yeah, 101 I did.
Okay. Yeah, 101's just one of those crazy Atwood ones where there are 3 blocks all combined, but you still keep in mind the same concept as any multi-mass Atwood system. Tensions are going to be the same from block to block. Now, because we have a 3-mass system, we do have to be careful with one thing. The tension that connects block A and block B have to be the same, and the tension that connects these blocks have to be the same. Acceleration has to be the same throughout, because they're all connected. So, like, for example, if I found the A of this block, it would be the A of this one and this one. Okay? Or any combination of that. So, we'll keep that in mind. But this just becomes a lot to keep track of, basically. But it's doable if you take it slow. So it says for 101, blocks A, B, and C are placed, as in the figure, and connected by ropes of negligible mass. Both A and B weigh 25 newtons each, and the coefficient of kinetic friction between each block and the surface is 0.35. So that stays the same for all of them. Block C descends with a constant velocity. That's a hanging one. So good, we got constant velocity. Everything will always be equal to 0 on both axes when we do Newton's second law. So the first thing was just simply what I did first, draw a separate free body diagram showing the forces acting on these objects. And it actually says just acting on A and B, but I did it for all of them because it's all relevant. So block A, we'll call the tension between block A and block B, I called it tension 1. That's to the right, it has friction to the left, and we got the normal force and weight there. Block B is on an incline, so we have tension of those and the tension of this one pulling backwards, plus the friction pulling backwards. And because we have an incline, the normal force would have to balance with the weight Y component of the weight for block B. And we have another one here. Don't forget that the horizontal component of weight, FGBX, or parallel, if you want to call it that, is also trying to pull it this way. So we have 3 forces in this direction on this block. So we got to identify all these. And the hanging ones are typical hanging ones. The tension up, tension 2, and the weight down. So this is just going to be just being really careful with keeping track of everything. So there's our free body diagrams. Block A and B both weigh 25 newtons, but we don't know what block C is. We're going to be asked then in part B to find the tension in the rope connecting just these two blocks. All right. So I'm going to set up Newton's second law dealing with just those for part B. So on block A, we have tension to the right minus friction to the left. And that means tension 1, once I break down friction in μk times the normal force, and over here I prove the normal force is equals to the weight, which by now should hopefully be obvious, but I still proved it out there. And μk was 0.35 for all of them, and the normal force balances with the weight of object A, and the weight of object A, as told, is 25 newtons, so we plug that in, and we immediately get tension in the first rope. So part A wasn't too bad, or part B, excuse me, finding that tension in the rope. Then we go on to part C. What is the weight of block C? All right. So if we go directly to block C, the only two forces on it, don't forget about the redirection of everything. That makes down positive, since if we're calling to the right positive all along here. So that's going to be the weight of block C minus tension 2. Equal to 0 because of constant velocity. Flip that over. That means the weight of block C must equal tension 2. And that's what we're looking for. But we don't know what tension 2 is. So tension 2 connects it with block B, so there must be something going on with that. So we got to go to block B and set up the sum of all forces, both x and y axis for it. Let's start with the x axis. Remember, we have the tension 2's up the hill, and as I noted earlier in the free body diagram, 3 forces trying to pull it backwards. Tension 1's resisting it. We just found that, so we have it. The friction between block B and the incline, which still uses the same u value as told. And the x, or parallel component, of the weight is trying to pull it down, so we subtract that off, but it's still all moving at constant velocity, so that equals 0. So I could start trying to solve for T2. When I do that, like I said, I know T1. I know that the friction, kinetic friction of block B, is equal to 0.35 times the, not the weight, but as I proved up here, it's equal to the perpendicular, or y component of the weight, which is the weight of B times the cosine alpha, and alpha was 36.9. So I showed that there. That gets plugged in for the normal force here. And then for this x component of the weight is the weight of block B times the sine of the angle plugged in there. So it's just a lot of little steps, but we have all that information giving me that tension 2 must be 30.8 newtons. And if that's 30.8 newtons, we already proved that that also equals the weight of block C, as we proposed up here. So I have on here, super awesome problem. It all connects. It's hard. It's harder. I mean, the concept's no harder than any other one. It's just keeping track of everything and making sure you never missed any of the forces, especially on block B. That had the most ball forces going on. But I mean, if you could handle a Atwood system like this, you could handle any Atwood system. There's a lot going on that. You okay with that one now, Spencer?
Yeah, I'm good.
Okay. You have anything else?
No, that's all.
Okay. All right. We're down to only a few minutes. So remember, tomorrow's test is all open notes, open Chromebook, open book, open everything. So you do not have to turn your homework in until I see you in person again. Okay? So make sure everybody, whether you're in person or at home, the test is going to be posted on Classroom. It's going to give you a due date for the end of the school day, and I think I marked that as 12 o'clock, lunchtime, on Wednesday. Okay, so you have Tuesday to work on it and Wednesday to work on it.
Was Wednesday only half a day?
Yeah, Wednesday's a Friday schedule. So I guess technically this year you'd be out at 11, but I'd put the cutoff time to turn it in and not be marked late as noon. Okay, but there's going to be no other things assigned on Wednesday. Just if you need that time to keep working on this, keep working on it. Okay, and again, do it however you want. Probably the best way is to do it on paper and take a picture and upload it. If anybody out there wants to do it on Squid, that's fine too. Just be neat, and no matter how you do it, circle your final answers. Okay?